So the screen recording is in session, so I think we should be as well. All right. So are there any questions about the homework assignment other than when is it due? Any questions about the homework assignment? Yep. Yep. Yes. Oh, I haven't. Find max 2? Other than what we talked about last time? So maybe okay. Well,
breaking it down the way you broke down the other code?
Okay, what I will do instead is to show you where you should look in the notes. Because basically it's a step-by-step process using those quote-unquote mechanical steps. Okay. So let's go to the website first, and then today we'll also have a few things to do, including going over the, what am I doing here? There we go. All right. And I can maximize this screen. Nice. All right. So there are a few things. First of all, I want to let you guys know where we are at this point, in terms of notes, what you should be reading, and also what is next. Because we are pretty much done with a very important piece of this class already. So we are done with topic 2. We're done with topic 3. We are done with topic 4, which is something that you need to understand in order to get into topic 5. And we are now close to finishing topic 5. Okay. So for the homework assignment, for the previous one, which is Find Max 2, and also for the current homework assignment, which is Find Max 3, you need to read notes regarding topic 4 and also topic 5. Now topic 5 may look a little confusing because there are 2 notes related to control structures. So what I'll do is I'm going to open up 2 tabs. One on this one, which is the newer one, and one on this one, which is the older one. Okay, they are basically the same thing. What these 2 slides would do is basically the same thing. They are both designed to help you understand how to translate C code or any high-level code into assembly language step by step. Okay, and I think last time we talked about conditional statements. Okay, so basically what you do is you start with structured control statements, like conditional statements. And then you look at this construct. I'm going to use the highlighter on the browser to highlight what I'm talking about here. So you look at this really well-constructed structured C code, and you say, well, it's not helpful if I need to translate this into assembly language, because there's no such thing as an if, there's no such thing as an else in assembly language program. Okay? The only thing you can do as far as conditionally going to some place other than just the next instruction would be the conditional branch instructions. Okay? Now, what type of conditional branch instructions do we have? That's in topic 4, but just to give you a summary of all the instructions that we have, they all start with J, for jump. So we have JZ, JNZ, jump if the 0 flag is set, jump if the 0 flag is clear, JC, JNC for the carry flag, O for the overflow flag, sign, and then you can combine these 2 to JL, JNL, that's JG, that's JNG. Okay, and then you can also combine JC and JZ. These 2 can also combine to J. Well, the JA is one, and then JNA is the other one. A stands for about, and then you can JC is the same thing as a JB, which is also below. So these are the conditional branches that you can use when you do your homework assignment in Find Max 3. Yep.
When I was using the E flags, when I was searching E flags, I kept getting a P flag.
E flag?
A P.
A P?
Pop up, yeah. I would say PF. When I would do IRE flags, I would see PF on it.
Yeah, the P flag is not one of the flags that we need to pay attention to.
Oh, okay.
Yeah, you can look it up and find out what it means, but it's not
It
important.
doesn't have, it wouldn't help us when dealing with jumps.
No,
Okay.
not with the homework assignments that we have.
Okay.
Yep. So with the homework assignments that we have, these are the conditional branches that will be useful. But the whole point is, we don't have if. Do you see if here? No. Do you see less than symbol here? Greater than or equal to? Not as symbols, but we do have JG for greater than, JL for less than, NL for not less than, NG for not greater than. Yep.
Is not less than mean greater than?
No.
No, it's not less than.
And it can be equal to. So don't forget the equal to.
So it can be equal to or less than.
J and L is done with not less than, which is the same thing as a greater than or equal to.
Okay, got it.
Not less than is the same thing as greater than or equal to. Okay? So those are the conditional branches that we have, and we can only construct, useful, meaningful control structure using these ones, and also on top of this we have the unconditional branch expression jump itself, which is also useful because sometimes you just need to do something like this. Now obviously this one is not necessarily needed, because if you really want to do an unconditional branch, you can always say JCL1 followed by JNCL1. So these two combined is the same thing as an unconditional branch. But why do this when you can have that? Right? So basically this is all that we have for conditional branches. But everything that eventually boils down to a Boolean usually they start with a comparison. Okay? So when you have a comparison, that means this is one family of instructions that you will need for control structures, and then the other one single instruction that you need so that these will be useful for whatever purpose you need it to do would be the CMP instruction. Because there's no point in using these instructions unless you utilize the flags right after a compare instruction. I mean, surely the add instruction and the subtract instruction will also change the flags. But most of the time, when you want to compare and say, okay, is X larger or is Y larger, you're just comparing. You're not subtracting. You don't need to store the result. You're not adding. So that's why compare is far more useful than the other two instructions when it comes to conditional branches. Are we doing okay so far with these instructions? Now CMP, just like the other instructions, it can take on the width operation or the width specifier. B for byte, W for word, 16-bit, and L for long word for 32. Okay, I strongly suggest that you have a habit of specifying the width of the operation manually instead of using it implicitly, using the register to imply the actual width. Always specify the width manually and think about the actual width that you need for the application that you're dealing with. Because later on when we perform other types of algorithms, you will have to specify which width to use specifically. Because otherwise you might be comparing to the wrong thing, okay, or using the wrong width for comparison. Right? So are we still doing okay so far, with the most basic building blocks of quote-unquote conditional statements? So getting back to the projector, a conditional statement in C starts like this. It's very structured, because block one itself can be a while loop, can be multiple statements, can be another conditional statement. That's why it is called structured code. Okay, but we cannot write structured code not supported by the language in assembly language programming. There are no curly braces. Okay, so that's why the first thing you have to do is to take this code that is written in C to begin with and translate that into also C language, but not structured anymore. It is not structured anymore because the curly braces are now gone. Okay, so that's why it is not structured anymore. But what about block one? What if block one is a conditional statement itself? Apply the same technique to block one. Okay? That is basically how we do it step by step to break down a program written in a high-level programming language into smaller blocks and then smaller blocks and then smaller blocks until the smallest block can be implemented using a combination of the compare instruction and one of the branch instructions. Are we doing okay so far as the overview of this stuff is concerned? Okay. What if you have a conditional statement that has, okay, well, before we move on any further, are there any questions about the equivalency between the original code, which is what Iraj or Damon or Professor Fox would expect, to this block of code where you will probably get points taken off because you're using goto and labels? But are there any questions about why the first block of code is functionally the same as the second block of code? Okay. Yep. What? No, nothing here is an assembly language. And that's the whole point. I don't need to drop down to assembly language until the very last stage. So you can do all the translation and double check that your program is still functioning the same way until the very last stage where you translate it into assembly language. In other words, if I give you a program that is well formed as a structured code, you can test it as the original C code, translate it to the highlighted block of code here, and test it again just using C and C++. Because they are supposed to be functionally the same, and we are still using high-level programming languages here. Am I still making my point okay? Sort of? Okay. So that means you don't have to deal with assembly language program debugging until much later. We want to defer that process as late as possible. If you have a conditional statement that only has a then block but without the else block, it translates to something that is a little bit easier, just like that. Any questions about this slide? So this slide does not seem like it has anything to do with assembly language programming, but it does, okay? Because if you apply this technique, eventually you will get down to a block, the kind of block of code that can be done in assembly language. Next slide. We have a loop here. Okay, last time we did not talk about loops because I did not have enough time to talk about the other control structures. Are there any questions about the basic while loop in C? How it works, the syntax, and just basically how you use a while loop in a program. Are there any questions about that? Very good, because if anyone asked me questions like that, I was about to send that person back to CISP 360. But Tag, I never took that class to begin with. Well, the more reason you should be going back to that class. Okay, now this part is new in this class. Okay, the original block of code, which is while C block 1, can translate to the highlighted block of code here without any loss of functionality or behavior changes. Is everybody convinced that this is how a while loop can be implemented, but using gotos and labels? Okay. So L1 marks the beginning of the while loop, so it gives us a point to go back to later on. And then we have a conditional statement that has just a condition and a goto, because we want to translate everything into a condition and a goto, because eventually they become something like this, a conditional branch instruction. And that's why we want everything to translate to if blah 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 go to a particular label. Okay. In this case, we have to negate the condition C, because when you have a while loop, C specifies when to stay in the loop. In this case, when we translate it into the unstructured code, we use the negation of C so that we control when to get out of the loop. So when not C, we go to label L2, and label L2 is after the entire thing. If C is true, then we are not going to L2, we perform block 1, and then right after block 1, we have an unconditional go to back to L1 so that we reevaluate the condition and then see whether we have another iteration to perform. Are there any questions about the equivalency between these two blocks of code? No questions? Okay. And then the last one is a post-checking loop in C. We have a do block 1 while C, and that translates to L1. Once again, L1 is used to identify the beginning or the entry point of the loop. and then we have block 1. And then at the end of this one, we have if C go to L1, because while C means as long as condition C is still true, we want to perform another condition, another iteration. Are there any questions about the equivalency of the first block of code, which is structured, as opposed to the second block of code, which is unstructured?
Why don't you ever have this like binary to C comparison between the two?
Huh?
Why don't you ever have it binary to C between like C and binary? Because like in assembly.
In assembly?
Yeah. Like why don't you have
But this has nothing to do with assembly. This translation works in C as well. If I give you a C program using the nice structured code, you can translate it into the second form, which is not structured, using go-tos and labels, and still have a C compiler or C++ compilers to compile the program and verify the behavior of the program has not changed, only because of the translation. Is that okay so far? Okay. So now we have covered all 3 major control structures in C and C++. Attack! Don't you know there's a for loop in C2? Well, I guess I do, but what is a for loop? A for loop is a glorified while loop. Exactly, it's a pre-checking loop, so I'm not going to cover that. Okay, because you can functionally do the same thing. You just have to move the blocks around a little bit so that you have the initialization, you have the step, and then you have the condition. Okay, same thing. It's just the placement-wise is different. What about a switch statement? Ha! Got you this time. What about a switch statement? You can do it with a conditional statement, nested conditional statement. So that's why I only go over conditional statements, pre-checking loop, and also post-checking loops. Everything else we can use one of these 3 to emulate. All right. So we now have the ability to translate structured code into unstructured code, but we still have a problem, because the problem is, what if condition C is complicated? If condition C is simple, we are done, right? Okay. So let's take a look at condition C here. So let's say C is simple. What do I mean by simple? Simple means it involves something here. Let's say it's a rectangle. It has a relationship. Let's say the relationship is represented by, I'm thinking of an operator that is obscure enough that it doesn't have any meaning. Fine. Okay, I'm running out of creativity. OP for operator. Okay. And then the second one is triangle. Okay. So if the condition C is something like this, it's simple enough that we can implement in assembly language fairly easily. Is that okay? Because it involves some kind of comparison and a conditional branch. Making any sense so far? Sort of? Okay. So what we need to do is now take a look at this one and say, how do we translate this into assembly? Assuming the rectangle block can be a register. If it's not a register, you can always put it into a register first before the comparison. The triangle one, same thing. Okay, if this is a really huge long expression, you can always store the result of the entire expression into a register. So now we are still boiling down to register compared to register. Okay. All right. So the way we structure this is we say CMP, specify the width of the operation. And the way we specify this in assembly language is we use the square first. Oops, I take it back. We have to flip the order. Okay, we flip the order. We have the triangle first as our first operand, and then the square block as the second operand. And then we have a conditional branch instruction here, and OP goes here. Okay. Go. And then we have label L something, because we are translating if C go to L1. So this type of construct in C translates to these 2 instructions in assembly. Are we still doing okay so far? Remember, you have to flip the order of the 2 operands, because we subtract the first operand from the second operand. That's why we have to flip them. Yep.
What's the comparison? What does that mean?
It's a placeholder. The square is the square. The triangle is the triangle.
I mean the
This one here
yeah.
specifies the width of the operation. depending on the type of the comparison. If it's char, you put a B here. If it's short or int 16, you put a W here. If it's just regular int or int 32, you put an L here. Are we still doing okay so far? Okay. What about signedness? What about signed versus unsigned? I mean, surely something here has to be dealing with, signed versus unsigned. Which part do you think specifies whether it's signed or unsigned after a comparison?
Flux.
It's OP itself. Okay? So in C, OP is either less than or equal to, greater than or equal to, and so on. And whether it's signed or unsigned, it is still less than or equal to, greater than or equal to. Right? In assembly, not so. Okay? We have signed less than, we have unsigned less than. Now, with all of these conditional branch instructions, which one is signed and which one is not signed? Not telling you, because I wrote it already in topic 4. Yep? Right. A, B, C are easy, so it's unsigned. So the other ones are signed. Okay, is that easy enough to remember? Unsigned is easy because you don't have to deal with two's complement and so on. So A, B, C is unsigned, and then the more complicated ones are the signed ones. All right? All right. Well, that's good. I mean, it is good if C is really that simple. It's just a simple comparison between two expressions. What if it is not? What if C involves logical or, logical and logical not in a big huge mess? That's okay. We got procedures to do that too. Okay, and that's also something that we went over on the other day. The day that you had to do a survey. Remember that? Did you guys enjoy the survey?
Wait, we actually did something last time?
Did you guys enjoy it? The survey? I don't even know what questions they ask you. No?
Enjoy.
Say again?
I said that depends on your definition of enjoy.
Ah, okay.
I mean, if it's English, then probably not.
I enjoy it as much as I enjoy iPhones.
Okay, point taken. All right, so what if the expression, what if condition C involves negation, disjunction, conjunction? Okay, well, we have ways to deal with it. This is something that we talked about last time. Let's talk about not first, okay? If you have a not in the expression, you can translate it from if not C equal to L1 to the following, which means if C branch around the go to the L1, that's functionally the same. Okay, but I would have let's just go through this stuff first, and then we'll talk about unnecessary steps like these. Okay, sometimes it's not necessary. What about disjunction? What if C or D is what you're looking for? How do we translate that and reduce the get rid of the operator? How do we get rid of the disjunction? Well, we break it up into two conditional branches. If C, go to L1. If D, go to L1. Okay? And also, this method also integrates lazy evaluation or short circuit evaluation right there. Because in C and C++ and all C-derived languages, short-circuited Boolean evaluation is a part of the standard, which means if C is true, we don't bother to evaluate D. But that logic is actually captured by this translation. Because if C is true, we go to L1 right away. We don't even bother to evaluate D in this case. And the last one is conjunction. Conjunction is the only one that is asymmetric and kind of looks weird. Because the way we do it is to say, okay, if not C, which means if C is false, we go straight to L2. We don't even bother to evaluate D, because with a conjunction, if the first one is false, the entire thing is false anyway. And using short circuit evaluation, we do not evaluate D when C is false to begin with. So we only fall through to if D goes to L1 if C is true to begin with. Is that making any sense? So in that case, if C is already true, then we only have to evaluate D If D is also true, then we go to L1, which is the original intent of the intent of the statement. If D is false, then we still fall through to whatever is followed. So functionally speaking, the original line of code using conjunction is the same thing as the 3 lines of code that we are translating. So using this process, we are adding additional conditional branches, other types of go-tos, but at the same time, we're getting rid of logical operators. Is that okay so far? Okay, because what we want to do is to translate everything. Everything has to be reduced to if some kind of comparison go to a particular label. Okay, and these steps will help you get to that goal. The next slide talks about how sometimes we do not have to go through all these trouble. In other words, sometimes we can apply different types of transformation so that we don't have to go through all that trouble to get things to work. For instance, if I say, okay, let me see if you guys can fix this one. Okay, I'm gonna write it on the whiteboard. Okay, not x is less than y, or x is greater than y. Okay. So if you just look at this logic here and try to apply the mechanical steps that we have talked about, you will end up with quite a bit of code. Okay, I would say you end up with maybe 7, 8, maybe 9 lines of code. I haven't done it yet, so I don't know for sure. Okay, but I can also translate this into one single line of code and done. Okay, so let's say the original code is if this entire expression goes to L1. How do I fix this? Say again? Yep, because functionally, this is the same thing as saying if x equals y, go to L1. Okay? So if you can do the reduction without having to go through those mechanical steps, even better, because that will save you a lot of time. But how well can you recognize something like this and do the reduction? Well, that depends on your experience with programming and logic and stuff like that. It is not necessary. If you want to translate this into 9 lines of code, it will still work exactly the same way, except there's a lot of extra work in that case. Does everybody see the equivalency between this long expression and just y, x equals y? So there are things you can do. There's De Morgan's law. There are other types of transformation in Boolean logic that you can apply in order to do the reduction without making the program more complicated. Any questions? No questions? So now I can throw any type of C construct to you, and you can translate it into assembly language.
You can use double and or double or.
Double and double or?
Like if x and y, and then if and, and then like a loop within an if within an if statement kind of, a do within a do.
Okay, now when you have nested statements,
Yeah, like a nested.
the most important part is how do you label the labels? How do you name the labels? Because in that case, just using L1 and L2 is not going to cut it, because you have L1s and L2s all over the place. So you will need to come up with a way to name the labels accordingly, so that when you look at the label, you know where it belongs. You can also use indentation. Even in assembly language programming, you can use indentation to help you understand where is this code located in the original C code. Any other questions? Shall we go through one example, just so that you can see the process and how it works? For C code.
You mean for nested statements?
For nested statements? Yeah, nested statements, exactly. Okay, so let's go through one example. And you know what? I'm going to borrow an example from cisp310. They just had this in the exam. And I'm not trying to, imply that you guys cannot do what cisp310 can do, because the point in this class is not to trace pseudocode, high-level code, is to translate it into assembly code. Okay, so it's definitely not an easy process. So I'm going to go through this process just to show you guys how to do it step by step. So we have, let's say x gets a value of 2, y gets a value of 0, while x is greater, okay, let's make it 4 here. While x is greater than 1, do the following. Y gets y plus 5, y gets y plus 4. If y is greater than or equal to 6, do the following. Okay, I'm mixing up my pseudocode with C code. Excuse my confusion here. All right. Well, because I'm using C code, I can do this. That's handy. And then we have x minus x here. That's good. All right. Let me magnify this a little bit because I think in the back it's maybe a little hard to see. Okay, so is that big enough? Especially people back there, can you guys read it? Okay. I don't see anyone with a binocular, like those opera house binocular, so I'm assuming it is okay. All right, so we'll go ahead and translate this into really badly structured C code because we'll just be using if, go to, and labels. Okay, and the last step to translate into assembly code, I'm leaving up to you guys because by the time you get to that point, it should be relatively simple using. Oh, I just erased it. The template that we have talked about a little bit earlier. The square, the direction is a triangle, and the OP thing. Okay. So we'll take a look at this code and see how we do it. You can work from the inside out. You can work from the outside in. It's entirely up to you to decide which way you go. Just don't start on multiple constructs at the same time. That would not be useful. Okay. I personally like to work from the outside in. So the way I do it is I will turn this entire program into comments. Okay, so in assembly code, I'm going to do it like this. I would use 2 pounds before everything because 1 pound is not enough later on in this class. So you might as well get used to the habit of using double pounds to comment out stuff that you want to comment out. If I were using VI, I could do this in one single command, but since I'm not using VI, I have to go through all this trouble. Yeah?
Why aren't you using VI then?
Because VI does not have a good contrast, on the projector. Okay, now we're ready. All right. X gets 4. Do we need to explain how to do that in assembly? No. So I'm not going to explain things that are not interesting, for the purpose of this discussion. So the first thing I want to translate would be the while loop. Okay. So I look at this while loop here. It starts here. It ends here. Whatever is in between is basically my block 1. Okay. So that way I can look up the earlier notes here and say, oh, okay, I know how to translate that now. Okay. So let's go ahead and translate the while loop first. So the first step to translate the while loop is to have a beginning label for the entire loop. I'm not going to use L1 for the beginning of the while loop. I'll just say while begin. Okay, so the label clearly indicates what it is starting and where it belongs. You should do the same thing too when you're writing your code, so that when you look at the label, you know the purpose of this label, which construct it belongs to. Okay. So right here, I say while begin. And also, because I know the structure of a while loop, I also need a while end down here. And right before the end, I have to go back to the beginning. I'm using the same indentation as the original code so that I know where the go-to belongs. It is the end of the entire while block. So this one goes to while begin. And now I can work with the condition part of the while loop here. So basically, the way I translate this is if not x is greater than 1, the negation of the condition of the original while loop, go to while end, like so. Are there any questions about this transformation?
So you write that into the assembly input.
Sorry?
You write that into the assembly input like that. You know, like that instruction.
No, this is in C code. This is not in assembly code. But when you look at, if not x is greater than 1, go to while end, you can translate that into a compare and a conditional branch instruction right there, because it fits the pattern that we just talked about. It has a single comparison, and you have a label to go to when that condition is true. So you have to remember the thing that we talked about earlier. Okay, I'll do it once. Okay, I'll do that translation once. Okay, so let's take a look at this one. I'm going to use it. I'm going to do it here. Okay. So I will translate this exactly once. And I'll also give you the template, so this way you will never lose it. It is all going to be on YouTube forever and ever. Okay, nobody can ever forget this one anymore. Okay, we need a placeholder for the first one. I'm going to use uppercase X as a placeholder, and I'm going to use OP to represent the comparison operator, and I'm going to use Y to represent as a placeholder for the thing that X is being compared against. Go to a particular label. I'll use L to represent that label. The question is, how do I translate something like that into assembly code? Okay, and the answer is CMP. You have the reverse X and Y, and then you have a conditional branch instruction, which is JOP in this case, to label L. Is that okay? It actually makes sense? Okay, well, that's exactly the same thing that I did earlier, except I had a square and a triangle. I would have used a square and a triangle if I could inside a plain text editor. But since I cannot easily do that, I'm just choosing not to do it. Okay, so in this case, I'll do it. Remember, I said I would do it once. Okay, so let's go ahead and do it. Yep.
Is JOP a real operator, or is that
No.
a placeholder?
JOP. J is J, but then OP is the placeholder of the comparison operator.
Okay.
Okay. So in this case, let's say, so let's go ahead and translate this one. Okay. The first thing I would do is to do something that you cannot do in C, is to put the negation here. Okay. In other words, I'm just saying that it is not the case that X is greater than 1. It's the same thing that X is not greater than 1. Is that okay? Because this way I don't need to go through the negation transformation, which is kind of troublesome. Okay. If I don't have to go through the transformation, I don't want to go through the transformation. Okay. All right. So let's translate this into the comparison thing. So we have compare. In this case, 1 is a constant, so it has to be an immediate operand, and X, is X. Okay. It can be a memory operand, can be a register operand. I don't care what it is. And then we have a JOP. So in this case, instead of using JOP, I'm going to do this. You cannot do this in assembly code, but instead, what do? What does it translate to in this case? Oh, not less than. We talked about this earlier. Not greater than is not greater than. Yep. Just how it's in this sentence. Not greater than is not greater than.
G and G.
Exactly. It's either J and G or J and A. Okay? So depending on whether X is signed or not, pick one or the other. So you have to read the notes. That's not entirely, but that's fine.
So what you could do is you could do JL and J and Z.
Right. Yeah.
Or
Okay.
Jay-Z.
So
Jay-Z.
is everybody getting this part, how to do the translation? Is that okay? All right. So remember, I will do this once, because from now on, you kind of know the approach, how to kind of format the compare instruction followed by the conditional branch instruction. Now, this is also a place where you will start to understand when you are doing things in C, what is done by an operator is not done by an operator in assembly code. In assembly code, they're all done by instructions. Okay, so it is the conditional branch instruction that is quote unquote doing the comparison and the conditional branch. It is the compare instruction paired with a conditional branch instruction that is doing the comparison and also the conditional branch aspect of a conditional statement. Is that okay? All right. All right, so now that we have this out of the way, let's work with the rest. How do we add 4 to y? Which instruction do you think will be useful for this instruction, for this line of statement? Add instruction, right? Add is add. Okay. Now this one is particularly easy because we are adding 4 to y. It is the same thing as y plus equal 4, which means after the addition, we store the result back into y, and the add instruction does exactly that, right? Okay. So it can be done with one single assembly instruction. That's good. Let's deal with this conditional statement here. Okay. This conditional statement is a structured if statement. We want to turn it into a unstructured conditional statement. When you turn this into unconditional or unstructured conditional statement, you start with the negation of the condition. So you say y, if not y is greater than or equal to 6, go to, in this case, and if. Okay? And the way I write programs, how you want to do it is up to you. But the way I do it is the moment I specify a go to, I immediately specify the label where it's supposed to go to. Okay, so this way I don't have to later on think about, oh, okay, I'm missing a label. Assembler is complaining I'm missing a label. Where am I supposed to put the label? I don't want to think about it later on. So as soon as I have a go to, which means I have an intent to go somewhere, I look up and say, oh, okay, end if is supposed to be here. So the end if label, marks the end of the conditional statement. So this is the way I would do it. This block of code, I think is fairly easy to implement in assembly. They can both be done by the subtract instruction. Okay? They would both use an immediate operand for the first operand and use a memory operand for the second operand, assuming y and x are memory operands. Are we doing okay so far? Okay. But Tack, you haven't explained about this instruction or this line here. How do we translate that into assembly language? Same thing that we did earlier, right? It is a comparison, a single comparison as the condition, and we have a go to as the action to perform when the condition is true. Well, it fits into the template that we can use one single compare instruction followed by a conditional branch instruction. Okay, so I'm going to do this. I just lied earlier. I'm going to show you how to do this one too. Yes, call me a liar.
Liar.
Okay, thank you. Return. What you just called, I'm going to return as a subroutine. Bad joke, never mind. If you don't get that one, I'm going to send you back to cisp310.
Jokes.
We have call in assembly. Call.
Hmm? Yes, we have call and return as well. But they are not actually necessary. There are ways to do it without using those instructions. All right, so we'll do this. It fits into the scheme of what we just talked about. So we have a single compare instruction, reverse the order of the operands. So we have $6 y, and then the conditional branch instruction is exactly the condition or the comparison that we have. So the first thing is to move this into here, okay? And then you look at this big mess here. What is there an easy way to say that? Not greater than or equal to. Exactly. Okay. So we have a jump if less than to and if. Are we doing okay so far? Basically the approach, it's not the specifics, but the approach of doing the translation.
Pseudo assembly. Pseudo assembly.
Yeah, pseudo assembly is probably the right term for that. But I don't want to give away the entire solution, so so the less than translates to, once again, one of these things. You can make your own little table and say, okay, follow these steps and translate it one step at a time.
So for this assignment, if we're not 100% sure about our answer, but we want to show the score in comments in the assignment, can we do this question by the course, is it right or wrong?
It's right or wrong for this assignment. We are not quite to the point of, show me the code and you pass your credit. Okay? Now, you can debug this step by step, okay? Because you can do it all in, unstructured C code, double check that your program works fine until the very last moment before you actually have to do the translation. Does everybody understand what I mean by that? Okay? Because, I'll just point out what you can do in C and C++. Okay, put the semicolon here. This is valid in C. Right? Okay, it's an if statement, it's a conditional statement with a goto as the then statement of the if. It's perfectly okay in C to specify a statement like that. It's perfectly okay to have a label definition in a C program. So this is okay, as a C program, as a part of a C program. In other words, you can translate it step by step, into the unstructured C code, all the way until you're ready to translate into assembly instructions, and double check that the program still does what it's supposed to before the very last step to translate into assembly code. And that's basically a process to write your program on in a step-by-step way, so that you don't do all the translations all at once, and now you have 25 lines of assembly code, none of which has been tested already. Okay, so you want to do it step by step, make sure that your unstructured C code is functionally the same thing as the original C code, and then you translate it into assembly. Are there any questions about the approach of breaking down a high-level program into assembly code? Any questions? Now, in this class, I'm not going to give you something like with 4 levels of embedding the if statement inside a while statement, inside another if statement, inside another while statement, because to me that's really just 4. Okay. But I will give you, something like this, with 2 levels, maybe even 3 sometimes. Okay? But most of the time, it's going to be simple enough that I'm just testing whether you understand how to do it, and not, how many labels can you track manually all at the same time. That's not programming. That's memorization. That's what Rayman does, not programmers. Does everybody understand the reference to Rayman? Because I want to make sure that we don't have any unresolved references. Label undefined, linker error. Sorry, bad joke. Okay, so are we okay?
For all these bad jokes.
Yes. Somebody can make a make a compiled version of all the bad jokes.
What is Rain Man? Is it a movie?
Rain Man is a movie.
Okay. He memorizes a lot of stuff.
It's got some illness, but it's helping.
All right. So with that out of the way,
Okay.
let's see whether I missed something in this particular slide. Oh, comparisons, general compare. Okay.
Tom Cruise is in the movie too. This is brother.
I lied one more time because I said last time was the last time I will talk about this. I'm talking about it again in the notes. Okay. So in general, if you have x, y, and the relationship, which is a comparison operation, and go to L1, you translate it into this code here. So this code in C translates to something like that. Okay. So yes, I lied again.
What's the JR look at?
R is less than or equal to, greater than or equal to, equal to, not equal to. Hmm? The operation, right? So R is a placeholder of the relationship operator, and then X is a placeholder of the left-hand side, Y is a placeholder of the right-hand side. Sorry? Yeah, the square and the triangle. Yeah. Yep. And there's a concrete case, right after this. So we have a concrete case of, if Y is less than or equal to 5, go to label L1, translates to this. Because less than or equal to is not greater than. And in this case, I have the assumption that Y is a unsigned number instead of a signed number. Right? Any questions? No? Okay. So let's double check and make sure that I cover all of this stuff about nesting and labels. This part only talks about conventions that you might find useful. One is the use of indentation. Even though the assembler does not care about indentation whatsoever, I think just for your purposes, you should use indentation whenever possible, so that just by looking at an indentation, you know which code is at which level. Okay? Sorry? You can only have one assembly instruction on one line, so you cannot really string multiple instructions on the same line. So use indentation to help you. And also the other thing that I recommend personally is to interleave your code with the original C code. So that way, you have the original C code around, close to your assembly code. So it becomes easier to remind yourself, okay, what are these two instructions doing? Oh, okay, it's implementing this construct in the original C code. So I personally find it useful, to have my C code in comments interleaved with the assembly code that implements the C code. But you may or may not find it useful. That's entirely up to you to decide how you want to do it. Use label names that are useful. Loop begin, loop end, begin loop, begin end loop, stuff like that. Okay, basically things that you can look at the label and it tells you what is the purpose of that label. Okay, L1, L2, they're fine, for examples, but they don't really tell you what the labels are really useful for. Sequential numbers. In this case, I have two consecutive conditional statements. So I would probably call the first one, conditional statement number 1, and I have a suffix for the labels for conditional statement number 1, and the second conditional statement is conditional statement number 2, and I use a suffix of 2 for that particular conditional statement. Use some way to help you to remind yourself which conditional statement we are talking about. Okay, you may have a different way of creating the label names, systematically. Whatever way you want to use is fine, as long as there's a way to do it. Okay, do it systematically. Any questions about all these slides? None of this is really technical. It's really just recommendations, so that when you go through the process of translating C code into assembly code, you don't run into problems of, oh, great, now we have L1 to L99, but which one is doing what in the program? Okay. The last one is nested constructs. So nested constructs should technically use a suffix and prefix notation to indicate how they are nested. In other words, in this case, we have and if inside the loop, because this is a conditional statement inside the loop. So I have loop ones and if one, because loop one means the first loop, and then if one is the first conditional statement inside the loop. So when you look at the label name using this particular method, just from looking at the label name, which construct within which construct within which construct compared to the original code. But it is kind of tedious, so you may or may not want to do it this way. Okay, when you have complicated programs where you have multiple conditional statements, that is at the same level, they're all inside a while statement, and the while statement is inside another conditional statement, you might find something like this to be more useful. Okay? Are there any questions about all of these things? All of the topics that we have talked about so far? No questions? back up. And oh, we missed one. Boolean operators reduction transformation. We kind of talked about this already. Boolean operator reduction transformation are low-level transformations. As such, the labels generated as a result should simply add a suffix to the original label. So in other words, if the original label that we want to go to is nif2 loop 5, because it is the fifth loop inside the conditional statement of the algorithm that we are implementing. So if the original label name is like that, and you have to add additional suffixes because you have to create a label, I would just add a suffix to it. Okay, so this way you still can find out okay, where is this code supposed to belong to? Well, it is supposed to belong to the fifth loop of the second conditional statement of the entire pseudocode. Any questions? I know somebody in this class is just going to use L1, L2, L3, L4, and so on.
I use 1, 2, 3, 4. I use 1, 2, 3, 4.
1, 2, 3, 4. So you're using base 4.
Yeah, and
so
you can use as many as you want.
So you have 1, 2, 3, 4, and then 1, 1, 1, 2, 1, 3, 1, 4, and then 2, 1, 2, 3.
You need to go like 1B, 1, 4, F, 4 part.
Okay.
Or above.
Okay. As long as you have a systematic way of naming the labels, it's good with me. Okay, I'm not going to grade your homework assignment based on your labels.
Because if you use like L1, L2, you need to have just one. You can if you use second time, you can use the second time. For
you
example,
cannot use it the second time. There's no such thing as scope.
Yeah, but you can use 1, 2, 3 the second time, the third time.
Right. All right. And apparently I lied one more time. I think my lying is becoming recursive. I lied that I lied that I lied that I lied. Did I lie?
You lied about lying.
So did I actually lie in that case? If I lie about lying? The fact that I did not tell the truth was not the truth. Never mind. Double negation is positive, right? Okay, so the reason why I said that is because I gave you one example like this, and I went through the whole process to do it step by step, and this time directly into assembly code too. Okay, so if you kind of just go through this, I go through all the transformations that we talked about in this class, and it's all step by step. I did not skip any steps. Okay, so I think that's that's going to be useful as long as you spend the time to read it. Where is this? This is okay. Let's go back to the. This is in topic 5, control structures. Okay. Are there any questions about the last portion here, which is just a long, huge, long example, and I also kind of follow my own advice of how to name the labels and so on. So you might want to read through this, and I think the final version is all in assembly code. Yes, it is all in assembly code. Okay, so you might find this example useful, when you have to translate C code into assembly code. Is that okay? So now we can move on to something else. Okay, we'll move on to talk about something that some people probably have been trying to do since day one for debugging purposes. Where's cout or printf? Well, there's no such thing as printf or cout in assembly language programming, okay? Because it's very primitive. So what we are doing now is we are moving on to the next topic. We are done with topic 5. Control structure is done. Okay. We are moving on to topic 6. And let me turn on the editing, and then we can highlight topic 6 is now our new topic. All right. Topic 6 has a whole bunch of little topics. But what is the main? Yep, go ahead.
What are we going to go over the exam systems?
That's a good point. Next time. Next time when I have it actually graded, then we can talk about the exam too.
That's what I was gonna ask about when you're gonna actually have it graded.
I have another class, another exam, that was done before this class exam, so I have to get it out of the way first. I will go back and look at how long it takes for me to grade one question, because it's unbelievably long, and this class is also unbelievably large.
Once you skip that name.
So topic 6. Topic 6 talks about how do you interact with an operating system. What does that have anything to do with cout or printf? I just want to print the value of something so I can debug my program, because I don't want to use GDB. So why do I have to understand how to interact with an operating system to understand how to print something? Exactly. Okay? Because the way you print something to the screen is writing something to a file. Okay? What is cout? What does cout do in C++? Prints to the screen is what it appears to do, but actually what is it doing? From the operating system's perspective, what are you actually doing when you say cout less than 5?
It writes whatever you're saying to a buffer and then moves it from the buffer to standard out.
To standard out. Exactly. Okay, the key word is standard out. Okay, there are several files that are pre-opened for every process. Okay, we have cin, cout, cer, and then, well, excuse me, not C because I'm thinking in C++. Standard in, standard out, standard and standard aux for auxiliary output. Okay, so those 4 files are always open for any process. Okay. So when you want to print something, quote unquote, print something to the screen, what you need to do is to write to standard out. When you want to see what the user has typed on the keyboard, you want to read from standard in. Okay, so those are file operations. Why do you think file operations have anything to do with the operating system?
Because isn't that how it sends data, like to memory, and then retrieves it and sends it to the other parts?
Because any file operation is an in operating system operation. Okay, why do you think that's the case? Why do you think any file operation should go through the operating system? But what about files in general? What is a file in general? Go ahead.
It is allocated memory that is given a certain name and is managed by the operating system
Right.
to avoid conflicts with other files and overwriting from other
Exactly. Okay, the job of the operating system is to make sure everybody play by the rules. Okay, so every process has to play by certain rules so that they do not clobber on top of each other. So we'll go back to an even more, rudimentary question. Okay, the more fundamental question is, what is the operating system doing, regardless of Linux, of Mac OS 10, or NT kernel? What do you think is the job of an operating system? Say it.
Management and organization.
Management and organization of resources, right? Okay, fine. You have 16 gigs of RAM on your computer. You have a 4 terabyte hard drive, and all the resources that you would ever need to run any program. But how do you decide which sector to write to when you save a file? From the application's perspective, okay? From let's say Microsoft Word perspective, you're saving a file. You click Control S, you specify the file name, you specify the location, click the Enter key. Okay? Are you controlling which sector that you're overwriting on your hard drive? Why not?
Something might already be there.
Even operation system doesn't know which sector.
The operating system is taking over and say that, well, I can see that you want to save this file. Let me handle that. Okay. Okay. So as far as you're concerned, you just need to know the path to the file. Then you can locate that file again in the future. Is that making any sense? Okay. But why is that necessary? What happens when we do not have a file operating system? Okay, think back in the DOS days. Okay, you don't even think about Windows. Think back in the DOS days. What happens without DOS? What is DOS anyway? What is DOS? Other than 2?
Disk operation system.
No, but they just released the source code for MS-DOS 1.1 or 2.0. They just released the source code for MS-DOS.
Yeah.
Okay, but what does DOS represent? DOS stands for
Disk
denial of
operating
service?
system.
No, but that's a modern interpretation of DOS. DOS. Okay, but what is DOS? Come on, you guys know the term.
Disk operation system.
Disk operating system, okay? So with an emphasis on disk, okay, it's not just an operating system, it is useful for disk management, okay? So imagine without DOS, you have individual applications, okay? So let's say you are writing the program, you're writing a particular application program on a computer with tons of resources. You have RAM, you have nice, good, high resolution screen, you have a lot of storage. What are you going to do to save a file? Well, now you have to decide which sector to overwrite to represent the directory, the file name, which sector to overwrite in order to store the content of the file, right? And remember, you are one of the applications that may run on this particular computer. So let's say the user closes your application, so now you're gone, and start another application. The next application starts up, and the user says, okay, I'm done with my spreadsheet, it's time to save the file. The spreadsheet decides that it's not going to play by your rules. Okay? The spreadsheet says, I have a much better way to make use of your 3 terabyte hard drive. I'm going to save the folder here, and I'm going to save the file over here, and all the access control stuff, I'm going to put it over here. With complete disregard of what you have done as a word processing program. Would that be a good scenario? Probably not. Okay? And that is why a file access is actually a core function of an operating system. Okay? Yep.
Are you talking about what? Access folders and stuff? Like folder A contains file B?
I'm talking about that. I'm talking about file allocation table. Which sector is in use?
That's a bad example.
It's a bad example, but it is still a standard that DOS is implementing for every application program that runs on top of DOS. So that when you have Excel running on top of DOS and you have Word running on top of DOS, when they save files, they play by the same rules and they do not overwrite stuff written by each other. Okay? So that's the function of an operating system. All right. And that's why file operations, even writing to quote unquote writing to the screen, which is the console, and reading the keyboard, which is reading the input file, those are also managed by the operating system. So the next question is, but how do we communicate with the operating system? Do we call something to request something, or what do we do? Okay, so let's think about that. We only have 5 minutes to go, so I don't have enough time to get into the details. Okay, of why we need, of what to do, but I need to explain why we need to have protection. Okay, so let's just say that we all understand function call, right? Because in cisp310 you know about function calls. So let's just say that in order to interact with an operating system, all you have to do is to call a particular subroutine, and it'll be done. Okay, and everybody is running in root mode, okay, because you have full access to everything. There's no such thing as protected mode or protection from each other. Okay. Would that be a good scenario? Why would that not be a good scenario? If I want to save this file, I'm going to save that file.
What if I also want to save it there too? What if I want to save it there too?
Okay, that's one reason. What other bad things can happen? When you just when you want to do something, you always get through, but that's something that you want to do. Malware. Malware. Yep, that's one thing. Why do you think the operating system needs to have protected mode? Yep. So you don't overwrite the data of somebody else's memory space. Okay. I know it doesn't sound like a long time ago. Remember Windows 98, Windows 95? Okay? What is the big difference between Windows XP, which is the first anti-kernel based Windows system for consumers, as opposed to Windows 98, which is the last functional operating system? I'm not counting Windows ME functional. Yes. Okay? What is the main difference? In Windows 98, if one application misbehaves, it can take not only itself down, it can take another application down, it can take the operating system down. Yep.
The NP kernel protected the entire operating system, so each individual program ran inside its own instance. Before the NP kernel was used, Windows, like if you were running programs on Windows 98, it would just crash the entire operating system.
Yep. Exactly. Now, if we go back even further, go back to Windows 3.1 and Windows 3.0, you know, they had quote-unquote multitasking. Okay, you can run quote-unquote multiple programs at the same time, and it seems like it works fairly well. But that type of cooperation is voluntary, which means if you are one particular program, one application running, you're one application running, and one application running, I need to say, oh, you know what? I think I have taken up enough processing time. I'm going to give up my processing time and give it to you. And you will do the same thing, same nice thing, and go like, oh, I think I just used the processing time for the past 20 milliseconds. It's time to move on. And the third, your process will do the same thing, and it will get back to you. This is called voluntary or cooperative multitasking. Okay. What if tech is nasty and say, you know what? I'm not going to give up the processing resources. I'm going to hog it and do whatever I want to do. I'm not going to give it up to you. Okay? What do you think will happen?
I'm not going to run.
You're not going to run, and neither will you. And I'm the only one who's going to run. Okay? And if I do anything funky, I can actually corrupt, Windows 3.1, the operating system. So the whole thing will just crash. I can end up writing some really bad content onto the hard drive, because guess what? I have full access to the I/O registers of not the IDE controller, because this is before the IDE controller. Is it called MFM? The hard drive, standard backend?
Yes.
Okay, so I have direct access to the MFM controller. So I can decide, you know what, I don't like those sections on this particular hard drive. I'm going to overwrite those things. Done, no problem. Okay?
The original Microsoft Word program.
Really?
Yes. If you were trying to say
If you try to badmouth Microsoft, it's going to erase your hard drive.
well, if you were trying to say use the Netscape browser at the same time you were using Microsoft Word 1.0,
Yeah.
then if you tried to save the file, it would take over the system resources, save the file, and then the Netscape browser crashes and the entire operating system.
Yep. Okay. So I think I have made my point about why the operating system needs to set up protection boundaries so the applications can only do so much. Okay. For certain things, if I want to overwrite a particular section on the hard drive, I can ask the operating system to do it, but you know what? If the operating system decides that's not a good idea, the operating system can come back and say, nope, we're not going to do it. Okay. So with that, ending this class, what we'll do about the next class is to talk about a mechanism where you can request an operating system, Linux in this case, to perform certain operations using certain instructions. So we are not calling anything. Instead, we're using a software interrupt to basically interface with the operating system. So we'll talk about that on Thursday, and also the visual editors. Are you going to 126, John? We are going to 126.
Yeah.